Okay, so if you found higher spin theories, the Veselier framework tough going, you can relax. The good news is that we won't need most of that for what follows, because we will be mainly concentrating on the three-dimensional case where things are actually, as we will see, much simpler. But of course, the reason to tell you about the whole formalism was that three dimensions is somewhat of a special example. The higher dimensional cases are obviously going to play more of a role as we understand things better. But in any case, let's start with the three-dimensional theory now. So the Veselier, so in AdS3, as you all know, gravity does not have any propagating degrees of freedom, and in fact, a simple counting of the degrees of freedom of these higher spin fields, namely that of a symmetric rank S tensor with a gauge parameter that's a symmetric rank S minus 1 field. So as we saw, the gauge transformation was at the linearized level something like this. So a simple counting of degrees of freedom, which if you're interested we can look at in the tutorial, shows that in three space-time dimensions there are actually no propagating degrees of freedom for any of these higher spin fields as well, like for gravity. But nevertheless, as we know for gravity, there's a rich theory which includes black holes in particular, the BTZ black hole, and we'll see generalizations of that, and also other non-perturbative solutions. So so even without propagating degrees of freedom, it has sufficient richness. And the other new feature about the three-dimensional higher spin theories, the Veselier theories, is that there is now a family of such theories which are labeled by a real parameter lambda. This higher spin symmetry that I introduced for you, which was essentially, so what the definition I gave you of the higher spin symmetry was to consider these oscillators, these spinor oscillators, which if you construct arbitrary products of them, there's an infinite dimensional algebra that you get from these oscillators. So that's in general dimension. In three dimensions, actually you can deform the commutation relations of that algebra by a single parameter, which I don't have time to explain the precise nature of that deformation, but there is a deformation of that oscillator algebra which leads to a one-parameter family of higher spin symmetries. So these are inequivalent symmetry algebras, and it's a special feature of the three-dimensional case. The other simplification in three dimensions is that the Veselier equations of motion become very simple. They essentially reduce to for these gauge fields A and A tilde. So okay, I should explain what A and A tilde are. So basically, in the Veselier framework, we had this C field which included the scalar and the generalized Weil tensors. Now in three dimension, as you know, the Weil tensor is 0. So in fact all the generalized Weil tensors are 0, and so that part of the Veselier fields is fairly trivial, except possibly for the single scalar mode. And then the other set of fields So we had the C field, and then we had this omega field, which was which contained the connection. So the C, as I said, is fairly trivial. There's just a scalar. And this omega, which is the connection field, actually also simplifies. Instead of the most general Young tableaus, I'll explain this a little bit more in the following slide. You have actually just the omega also essentially goes to just a generalized field bind and connection. So many of the additional auxiliary fields actually go away, and I'll be a little more precise about that later. And you can capture all the remaining fields can be packaged into sort of two gauge fields which belong to this HS lambda gauge group. Which, if you wish, are in the Lie algebra of this HS lambda. Actually, HS, so the reason there are two is that the symmetry algebra is actually HS lambda times HS lambda. It's a bit, this will probably become clear a little later. So the A belongs to one HS lambda, the A tilde belongs to the other. So the other point you should remember is that so this real parameter lambda fixes for you many of the other features of the theory. In particular, the scalar that's present has a fixed mass, which is determined by lambda and takes this form, and for lambda greater than 0, you see that this is above the Brighton-Lohner-Friedman bound, so which is -1 in this case for AdS3. So that's so the scalar has this particular mass. And by the way, I should mention the scalars are in some sense optional in this case, unlike in the higher dimensional case, meaning you can have a consistent truncation of the theory without the scalars as well. Though in the case we will be considering, the scalars will be present. In any case, the action for this theory is very simple, because the equations of motion are those of the equations of motion are just f of these f of a and f of a tilde equal to 0. This is just the curvature associated to these gauge fields. This is the equation of motion that follows from an action, which is the Chern-Simons action, which you have been hearing about in Marcus's lecture as well. But the only difference is that now it's a Chern-Simons action evaluated on an infinite dimensional gauge group, namely this HS lambda gauge group. And so this HS lambda might be a little mysterious. I'll tell you a little bit about what this HS lambda is now. So this lambda is a parameter. When lambda is equal to n, this HS lambda is SLN. So this is a particular case where the infinite dimensional algebra actually truncates to a finite dimensional algebra. So for discrete values of lambda, namely lambda equal to n, HS lambda is actually equal to SLN. And one way to think of HS lambda is as a continuation of SLN to arbitrary non-integer values. There's a more precise way to say this, which is to consider the SL2 algebra, which is generated by so the SL2 algebra, which is generated by J0, J plus, and J minus, and consider what is called the universal enveloping algebra of this, which basically means all the words that you can make out of these J0, J plus, J minuses, but modulo an ideal, or you quotient it by the second Casimir, namely the second Casimir of these J's, equal to square. So you quotient it by so you consider arbitrary words made out of J0, J plus minus, but whenever you get a combination which is proportional to the second Casimir of SL2, which is something like J0 square minus J plus J minus minus J minus J plus, you set that equal to this lambda square minus 1. So this is basically the HS lambda. There's a trivial identity piece which you sort of subtract, but for most practical purposes, you can just think of this as HS lambda. So this is the mathematical way to characterize what this HS lambda is. So it's a well-defined mathematical infinite dimensional Lie algebra. And so that's the symmetry algebra of these three-dimensional Vasiliev theories. It's just a somewhat unfamiliar symmetry algebra, but written in terms of J plus J minus, it becomes more natural, and it's not difficult to see then that when lambda is equal to n, this relation implies that what you get is SLN. So you always start with SL2? Yes, for this particular construction of HS lambda, yes. And what prevents you to do this thing for higher than that? You would get other groups, other infinite dimensional Lie algebras, but that's, yeah. In particular, there's a supersymmetric version of SL2, and the OSP 1, 2, and one can consider a similar construction that will give you the supersymmetric version of HS lambda, which actually appears in the supersymmetric Vasiliev theories. But the mathematical construction is very general. Any other questions? Okay, so in the case of SLN, let me first explain to you, though this will not be the case, I should stress, that we will be looking at, but since SLN is probably more familiar to you, let me first explain to you in the context of SLN, and then extrapolate to the HS lambda case. So in the case of SLN, when lambda is n, the spin content of the gauge fields is actually now truncated. So the Vasiliev higher spin theories, it turns out for these values of lambda, the higher spin fields have a maximal spin which is n. So you have all the spins from 2, 3, all the way up to n, and no higher. So this is again another feature special to 3 dimensions, where that you don't necessarily have to have an infinite tower of higher spin fields. You can sort of consistently truncate to a finite set, and that's related to the fact that with this relation, this truncates to SLN when lambda is an integer. So the action that I mentioned, the Chern-Simons, it's the Chern-Simons action now for the gauge field. So there are essentially 2 gauge fields, which maybe I should explain to you what these gauge fields are first. So to understand what to put this in maybe a more familiar context, recall this formulation of classical three-dimensional gravity, going back to Achukaro, Townsend, and Witten in 80s, who showed that the classical Einstein-Hilbert action on AdS 3 can be written as sum of two Chern-Simons actions with the gauge group SL2 times SL2, and the action was so there were two gauge fields, A and A tilde, which you constructed from the connection and the Vierbein, so two combinations of the connection and the Vierbein gave you two sets of gauge fields which belong to SL2R, and the Einstein-Hilbert action was just the sum of two such terms with sort of opposite levels, and the level of these Chern-Simons action was related to the AdS radius and Newton's constant in this particular way. So this is an old and well-established piece, which probably is familiar to most of you, about three-dimensional gravity. But one thing that I just like to remind you is that one of the important things about three dimension which enabled you to do this was the fact that you could trade this two indices of this connection for a one index object by using the epsilon tensor, and that's what allowed you to then form these combinations and multiplied by the SL2R generators, and SL2R was the tangent space group, or SO2, 1, and enabled you to write the action in this way. So what we have in the case of these higher spin theories, so let's first talk about the case when lambda is equal to n. When lambda is equal to n, this generalizes to, so this construction here generalizes, and now because in a very similar way, you can combine the Vierbein, the generalized Vierbein, which, if you remember, had these S-1 indices for the spin S field. And then there was a connection which was, so the first connection, omega, had one box here and S-1 boxes here. So that's the one, oops. So that's the one which you can actually dualize in the similar way and write it as this. And then all the spins from 2 to n can be put together into an SLNR, into a single SLNR gauge field. This is related to the fact that SL2, that the adjoint representation of SLN decomposes into a 3 plus a 5 plus a 7 and so on of the SL2, which is what these are. So that's the explanation of the fact that these generalized Vierbeins and connection, the only thing that actually survives are these two sets of quantities, these two objects, and they can be packaged into an in this particular case, an SLN a gauge field, and more generally into an HS lambda gauge field. And there are two of them. The two different signs give you the two separate SLNRs, or the two separate copies of HS lambda. So that's the general idea, that the non-trivial pieces of the Vasiliev higher spin fields, the gauge fields, are now can be realized as just regular gauge fields with a Chern-Simons action, but typically with an infinite dimensional gauge group. And in some particular cases with a finite dimensional gauge group. And the cases where you have finite dimension are the ones where the spins have a maximal, where there's a truncation to a maximal spin. Is that clear? So any questions? Okay, so this is the basic thing that you need to remember about three-dimensional Vassiliev theory. If you feel comfortable with that, then yeah. Yes, so the scalar field also, so this was, I looked at purely in the case of purely the gauge field, but you can take into account the scalar field. The scalar field essentially transforms in some kind of bifundamental representation of this, of these HS lambda gauge groups. And so in terms of the star product, there is an equation of motion for the scalar field, which is something like dc plus c star a minus a tilde star c equal to 0. I'm sorry? Only if so yes, only if lambda is equal to n. So you would have the scalar field will have a mass which is n square minus 1 for a very specific value of the mass. Any other questions? Okay, so that's the important thing about the three-dimensional Vassiliev theories. Now AdS3 gravity, you know, has an asymptotic symmetry algebra which is larger than the SL2R times SL2R isometries of AdS3. In fact, the asymptotic symmetry algebra is 2 copies of the Virasoro algebra, and the central charge is related. This is L is actually RADS in my notation. This is yeah. So this was the Brown-Hainaut result, and recently this was generalized to the case of these higher spin theories by the Potsdam group of Campoglioni and Friedenhagen, Thyssen, etc., and also by Hainaut and Ray, who actually looked at HS lambda, but at a special value of lambda. So what they realized is that the asymptotic symmetry group in this, so let's say, let's take this case for concreteness. The asymptotic symmetry group is actually a larger symmetry algebra that the so-called WN symmetry algebra of two-dimensional conformal field theories, and I'll say a little bit more about this later. So there is an extended symmetry algebra which contains spins s equal to 2 up to n, and this s equal to 2 case is the case of the stress tensor, but you have more generally higher spin currents, so what they showed was that the asymptotic symmetry algebra actually had this extended symmetry, which is larger than the Virasoro symmetry algebra. This was shown more generally for the general HS lambda theory, that the asymptotic symmetry algebra is something called is what's known as a W infinity algebra, with labeled by a parameter lambda corresponding to the parameter in the HS gauge symmetry, the HS gauge group, and the HS lambda sort of sits in its wedge, if you wish, just like SL2R times SL2R, which is the L0 L plus minus 1, which sits in the which is which is extended to all the L plus minus n. More generally, you can there's a parameterization in which the HS lambda generators can be parameterized by 2 numbers s and n, with mod n less than or equal to s minus 1, so this is the HS lambda generators, and the W infinity of lambda generators, you sort of remove this restriction, and you consider all Vns for all n. So the analog for s equal to 2, this would have meant that n is equal to 0 plus minus 1, which is the SL2R generators, and Virasoro is the one where you remove the restriction on n. And similarly, for the HS lambda generators, now you consider arbitrary spin, and you remove the restriction on the moding, and you have the W infinity algebra. So if you wish, that's the reason for calling it a wedge algebra. So this is sort of inside a wedge, whereas the full W infinity includes all the modes outside the wedge as well. Okay, so the asymptotic symmetry algebra is a much bigger symmetry algebra than the higher spin algebra, and by the same Brown-Hainaut type reasoning, any dual CFT must have this W infinity of lambda symmetry. This W infinity of lambda, by the way, I should have mentioned, was actually, as an algebra, at least as a classical algebra, it was studied by Figueroa, Faril, and others, but in the context of CFTs, it hasn't been very much explored. But there have been special cases, like the case where lambda equal to 0 or 1, this algebra actually becomes much simpler. In general, this W infinity of algebra is a sort of nonlinear algebra. It's not a Lie algebra like the Wn algebra in general. Namely, there are the commutator of two terms generates for you products of terms on the right-hand side. So it's not a Lie algebra, but for lambda equal to 0 or 1, it reduces to a Lie algebra, which actually governs the higher spin currents of free fermions and bosons in 2 dimension, as was shown much long ago by Pope, Romans, and Shen. So these are some facts about the 3D higher spin theories that I want you to keep in mind, and we'll come back to this soon. But now I want to. So this sort of completes my discussion of the Vasiliev theories in different dimensions, and now I want to start off on the different holographic dualities for these Vasiliev theories. But before that, any questions? Okay, so the original duality for these Vasiliev theories, so purely for the Vasiliev theories, was the so-called Klebanov-Polyakov duality for 3D vector models, for a 3-dimensional CFT. So the first thing, as I mentioned in the beginning, that if you want a dual to a Vasiliev theory, it clearly has to have a much smaller infinity of single particle operators compared to a gauge theory. So we saw in the Yang-Mills theory that the fields dual to the Vasiliev higher spin fields are a small class of all the fields in the theory. Namely, these are the twist 2 operators with 2 fields and many derivatives. Yang-Mills theory has gauge invariant single trace operators of the form trace phi to the k with many derivatives, so Yang-Mills theory has a much larger set of gauge invariant single particle operators, a Hagedorn density of them. So if we want a dual CFT dual to a Vasiliev theory, it must have a much smaller infinity of single particle operators, and vector-like models, in fact, have far fewer degrees of freedom. Vector theories, unlike gauge theories, which are matrix-valued theories, vector-like models have degree of freedom proportional to n, because they are the size of a vector, whereas gauge theories are proportional to n square, which in the large n limit is a big difference. And in fact, if you consider, for instance, a vector model of n component scalar field, the only single particle operators in the theory are these bilinears formed from the field phi I, because unlike in a matrix where you can contract the indices in many different ways, so you can have trace of phi to the k for a matrix field, and this is a gauge invariant operator with many fields. When you have a vector, the only way to contract two vector indices and form a singlet is to just have a bilinear of them. The other possibility is to have something like a baryon operator, which has some epsilons, but of course for scalar fields those wouldn't be there, but for fermions you could have them. In any case, those are objects whose dimension is like n, because they would have n fields. But in the case of the bosons, the only gauge invariant, the only singlet operators which are sort of single trace are bilinears. Any other operator would be products of these. So anything which is a singlet you would be able to decompose into sums of products of such operators. So the basic singlet operators are bilinears with many derivatives acting on them, and which are exactly these operators. So you can take as a basis precisely these higher spin currents, which we wrote down earlier, except that there we wrote it down for matrix valued fields. Here we are writing it down for vector valued fields. So I is a vector index which goes from 1 to n, and everything else is the same combinatorial factors, etc. So if these are the only single particle operators, then we are in good shape in matching the spectrum to the Vasiliev theory, because as we saw, as I argued in the first lecture, the corresponding the corresponding bulk fields are precisely the Vasiliev gauge fields, one for every spin. And in addition, you can have a scalar as well when s is equal to 0, which is, so you have precisely the content of the Vasiliev theories, namely the higher spin gauge fields and the scalar. So this was the observation of Klebanov-Polyakov and also Sezgin and Sundal. And the interesting thing about these vector-like models in 3 dimension is that they, so this, of course, in the free theory you have these conserved currents, but these vector-like models have actually a non-trivial quantum behavior when one includes interactions. Either you could consider an ON vector model like this, where I consider some real fields phi, or I could consider fermions psi. I could just replace my phi with some psi, and I would have the Gross-Nebo model. And when one includes interactions, these theories have non-trivial quantum behavior. For instance, if I add to the free action of the ON vector model a double trace-like interaction, namely a quartic term phi I the whole square, then it's a famous result that there's a non-trivial fixed point of the renormalization group flow, the analog of the Wilson-Fisher fixed point in the infrared. So you perturb this theory by this operator. It flows to a non-trivial fixed point, which can be analyzed exactly in the large N limit. That was one of the first things that was studied in the large N expansion of vector models. In some ways, you could say it was more or less the large N expansion was devised to understand this particular system. So what happens? This is a non-trivial fixed point. So the operators don't have their canonical dimensions. But what happens in the large N limit? Actually, quite simple. This scalar bilinear phi I now turns out to have a dimension equal to 2 plus 1 over n corrections. Instead of the canonical delta equal to 1. Remember that in 3 dimensions, phi has a canonical dimension half, so phi I has canonical dimension 1. So at the free or UV fixed point, this had dimension 1, but the large N analysis shows that in the infrared it has dimension 2. So the proposal of Klebanov and Polyakov was that both the free theory, so there are 2 conformal field theories in this system. One is the UV fixed point of the free ON vector model, and then there is the infrared fixed point, which is this Wilson-Fisher fixed point. And they claim that both these CFTs are dual to a particular Vasiliev theory. So both are conformal field theories, and they're both dual to the type A Vasiliev theory. So remember, I described in the case of the general Vasiliev construction that there was a slight freedom in your choice of your theories, and if you had parity invariance, there were essentially 2 choices in this phase e to the I theta, and one was the type A and the other was the type B. So they proposed that the type A theory with only even spins is the dual theory, and it has a scalar. The scalar has mass square equal to -2 in AdS units. So the difference between the 2 theories is that this scalar can be quantized in 2 inequivalent ways. When the scalar field lies in a particular window between the Brighton-Lohner-Friedman bound and a certain somewhat higher value, it turns out that there are 2 normalizable modes, and you can have 2 inequivalent quantizations consistent with conformal invariance. And they claim that depending on which way you quantized the scalar in AdS, corresponded to which of the 2 CFTs you got. And so the only difference this makes is the choice of the quantization only affects the dimension of the dual scalar bilinear, which is this phi I. The bulk scalar is the field which couples to this operator phi I on the boundary, and if you quantize it in either of the 2 inequivalent ways, you get either delta equal to 2 or delta equal to 1. In fact, as you probably know from AdS CFT, there are 2 values, delta plus and minus, which are sort of d by 2 plus minus something. They add up to d. They add so the 2 delta plus and delta minus add up to 3, and that's what you see over here. So in some ways, this is a small, not very non-trivial check of the fact that you reproduce this non-trivial scaling dimension from the Vasiliev theory by exploiting this choice in how to quantize the scalar field.
Rajesh?
Yeah.
What's the reason for ignoring the other deformation of this vector model, which would be a phi square cube deformation? This would be a marginal deformation. So in principle, you have a one-parameter family of such theories, right?
Yeah. So this would be like this would be a fine-tuned sort of. So you wouldn't flow to it from this UV fixed point. You would have to sort of flow up in the RG flow to a point which corresponds to that. But it's a good question. I think it has not been studied, and there might be something interesting to be understood there.
There's no symmetry preventing it.
No, not that I know of. So this was for the ON vector model, and there's a similar conjecture for the UN Gross-Neveu model, which is basically a vector-like model in terms of fermion size, and that is very similar. It again has two fixed points, and it turns out that to match with the spectrum of that theory, it's the type B Vasiliev theory that plays a role. So both the Vasiliev theories that you have in 4 dimensions have a candidate conformal field theory duals in terms of vector model CFTs, and the initial checks were, as I described, at the level of the spectrum, with the new thing being the spectrum of these scalar bilinears, because the spectrum of the gauge fields by construction agrees. They are conserved currents, so corresponding to massless fields, so their dimension is protected. So the spectrum matches to leading order in N. After all, on the Vasiliev theory, you only know how to compute the classical theory, so that's the leading order in N. So the spectrum agrees, but a very non-trivial check was the matching of arbitrary of 3-point functions of arbitrary currents, which you can compute on the boundary fairly easily, but from the bulk, it really uses the cubic vertices of the Vasiliev theory. Well, actually, I should say there are no cubic vertices, because I told you we don't have an action yet. They actually use the equations of motion and the sort of quadratic nonlinear terms in the equations of motion to actually compute this. So this is a sort of a bit of misstatement, but effectively the nonlinear terms of the Vasiliev theory play an important role in getting these to agree for arbitrary spins, and this is what I think convinced many people of the essential correctness of the Vasiliev theory as the dual, because this really used the dynamical content of the Vasiliev theory much more than just the spectrum, which and it was also later shown by Jiombi and Yin. So this calculation, this sort of very non-trivial calculation, was done by Jiombi and Yin, who then went on to also show that so they computed things in the free theory, but from the field theory point of view, you know actually that the correlation functions of the free and the interacting theories in the large N limit are actually related by a Legendre transformation. And they showed that this this change in the boundary conditions for the scalar effectively implements that Legendre transformation. So in a way, if you know, so what they showed is basically that if the correspondence holds for the free theory, it automatically holds for the interacting theory, because the free and the interacting theories are related by a Legendre transformation, and that's what the change in the boundary condition does for you. Okay, so this was the original Klebanov-Polyakov conjecture, but recently an interesting generalization of these vector models for the case of fermions. Actually, I should have mentioned also, so there's also a related work for scalar fields by the group of Ahroni et al. But in this particular case, actually, you get something interesting, and there's an open question, which is why I wanted to draw this to your attention. So if you consider these, the fermionic version of these vector models like the Gross-Neveu model, so you have vector fermions, and you couple them to a gauge field with a Chern-Simons action, so an SUN or UN Chern-Simons action, and if this parameter lambda, which also appeared in Marcos's talk, it measures now the strength of the interaction, you get a line of interacting conformal field theories, because basically thise this Chern-Simons action, when you couple to the gauge fields, you don't generate, you don't break the conformal invariance, and effectively, even though k is quantized in the large n, large k limit, this effectively becomes a continuous parameter, and there's a line of interacting conformal field theories, and an interesting question is to ask, what is the bulk dual of these CFTs? And this is not been answered. I mean, they were hoping to relate it to the Vassiliev theories which break parity, but that doesn't seem to work, so there is no answer known to this question of what the bulk dual is. There are some things that are known, namely that the spectrum doesn't get modified from the free theory, namely the dimensions of operators remain the same. However, correlation functions are no longer those of the free theory, and this is related to the fact that the higher spin currents are not conserved, and I mentioned this Maldacena-Zhibodev theorem in the beginning, that if you have higher spin symmetries in three-dimensional field theories, the correlation functions should be those of free theory. Here the correlation functions are not, so the higher spin currents are not quite conserved, but they are sort of broken in a mild way, and this may be therefore an interesting case to understand how you can try to use the power of the higher spin symmetry nevertheless to even though the symmetry is somehow broken, to try to see whether you can still say something about the interacting theory. This would teach us, I think, things about how this higher spin symmetry could play a role in, say, Yang-Mills theories away from lambda equal to 0. So I think this is a very interesting direction. Okay, so that's about the AdS4 CFT3 case. So we now I'll talk about come back now to the AdS3 Vassiliev theories and the dual CFTs. So we can sidestep this Maldacena theorem in two-dimensional CFTs because essentially because we know firstly that there exist higher spin the basic, just like the Coleman-Mandula theorem doesn't hold in two-dimensional CFT, the assumptions in the Maldacena-Zhebodev theorem break down in 2 dimensions, and indeed we know of examples which have interacting theories with higher spin symmetry, and therefore one can hope to have a candidate Vasiliev dual to even interacting CFTs, and we'll see that there are theories with these higher spin Wn symmetries which appeared already, these Wn symmetries which appeared already in this asymptotic analysis of this 3-dimensional Vasiliev theories. So this is so what I'll be describing is the work done with Matthias Gaberdiel, and maybe some of you have heard his colloquium yesterday also. But in any case, I'll let me first quickly state for you what the duality is, and then explain in a little more detail what the different ingredients are. So the CFT we will consider is a Coset-Weissimano-Witten model. Essentially this Coset, I will explain this in a moment. These are what are called the Wn minimal models. But what we will be taking is sort of an unusual limit, at least in the sense that no one has really looked. I mean, it's not a standard vector model, but nevertheless, the Stoft limit seems to make sense, as I'll describe. So basically, it's a limit in which you take these parameter k of this Coset model and take this ratio to be fixed. This ratio lambda will measure the strength of the interaction. So lambda equals 0 is sort of the free theory in some sense. So in the way I've defined it, it's slightly different from the way Marcos had defined it. It's now n over n plus k, so it lies between 0 and 1. And you get again in the large n limit effectively a line of CFTs with a central charge which grows like n. That's the sense in which it's a vector-like model. The number of degrees of freedom grows like n. And the proposed bulk dual is this Vasiliev HS lambda, this higher spin theory, where lambda is now the same lambda. So when I described this HS lambda theory, there was this real parameter lambda, which governed the mass of the scalar. It governed the gauge group. We identified this parameter lambda with this lambda over here. And it's a genuine HS lambda theory. It includes spins all the way from 2 to infinity, coupled to 2 equally massive complex scalar fields with mass square, which is the same mass that I wrote down earlier. So you can again quantize these 2 scalars in opposite ways, and they correspond to primaries by using the AdS CFT dictionary. If you translate this mass to the dimensions on the boundary, you find primaries which have this value, half into 1 plus minus lambda, and we'll see that those are indeed present here. And the central charge of the CFT we identify with the Brown-Heno, Campoleoni et al. Heno-Ray central charge, which is this. So that's just the statement, and I'll now elaborate various pieces of the CFT because I've already told you a little bit about the bulk dual over here. I'll elaborate a little bit on this, but any questions? Okay, so yeah. 5 more minutes, right? I started at 10 past, right? Yeah. So the G mod, so a Coset model more generally is a Weis-Zumino-Witten theory based on the gauge group G, in which you gauge a subgroup H without introducing any kinetic term for this subgroup H that you gauge. So that leads to another conformal field theory. The Weis-Zumino-Witten theory is a conformal field theory, but if you gauge the subgroup H without introducing any kinetic term, you do not break the conformal invariance, and you are led to another conformal field theory whose stress tensor, it's not difficult to see, is actually just the difference between the two stress tensors, and therefore the central charge is just the difference between the two Weis-Zumino-Witten central charges. So these are the usual Sugawara stress tensors of the Weis-Zumino-Witten theory. In some ways, this is a very important class of theories because it was studied extensively in the 80s as a sort of a building block for so-called rational conformal field theories by varying different G and H. So it's a very canonical set of theories. And we will be considering the case where G is SUN times SUN and H is SUN, a diagonal SUN. And we'll take this SUN to be at level K, this could be at level K and this at level L, and this could be at level K plus L. But we will consider the case where L is equal to 1. So one of these is 1, and additional L does not seem particularly interesting. So this is the so-called minimal model series. And if you work out the central charge using the prescription that I gave you, the difference between the G and the H central charges, you find a family of theories with central charge given by this. So if you keep n fixed and vary k, so I've written it here in terms of this combination P, which is k plus n, and you see that this is a family which accumulates at n minus 1, so its central charge is bounded by n minus 1. In the particular case of n equal to 2, actually this may be more familiar to people because this is actually the family whose central charge is 1 minus 6 over p into p plus 1. These are the so-called unitary discrete series of the Virasoro model. So this class includes the Ising model and other familiar models of statistical mechanics at criticality. For the general n, if you take k equal to 1, that's the first element in the series. That's also a fairly well-studied theory. It's the so-called Zn parafermion theory. It's a Zn generalization of the Ising model, which is the n equal to Z2 case. The k equal to infinity limit, that's the sort of accumulation point, is where you get the central charge is n minus 1. It's a bit of a delicate limit, but this has been analyzed recently by Matthias and Suchanek. And what one finds is that this is essentially the singlet sector of n minus 1 free boson. So it's also a reasonably familiar theory. So many things are known about these theories. I'll just stop in a couple of minutes. So the spectrum of primaries are labeled by two representations of SUN, lambda plus and lambda minus. You could parameterize lambda plus and lambda minus by your favorite way of studying representations, Dinkin labels, Young tableau. The integrable just refers to the fact that there's a bound coming from K, which will not be so important to us because we'll be taking the large K limit. The dimensions of the primaries, so the spectrum is labeled by these two representations, and the dimensions are given in terms of these representations in a fairly explicit way. So P is k plus n. This rho is the Weil vector of SUN. And so you just take the mod square of this combination of vectors in the Lie algebra, and you get an answer. For the case n equal to 2, namely SU2, this is much simpler. The representations are just labeled by each representation is labeled by one integer. So R and S, if I choose R and S as the labels of the two representation of SU2, then you get this expression, which is familiar to those of you who have studied two-dimensional CFT, the unitary Virasoro discrete series. This is this thing. And particular cases are when you take one of the representation to be the vacuum, the other one to be the fundamental, you get some expression, and the other way around, something else. But we'll come back to these expressions. At the moment, you don't need to, just to show you some explicit function, that there are easily writable explicit forms of these things. And the partition function, of course, is given in terms of contributions from each of these, and these are captured by so-called branching functions, which I'll come to next time. Okay, maybe I'll just state it quickly. The branching function also, the CFT partition function is the sum of contributions from each of these primaries with mod square of a particular object, the so-called branching function, which is known very explicitly. This is the Dedekind eta function, and basically this is a sum over the affine Weil group. So just to tell you that things are known very explicitly, you get what are the generalizations of the usual characters in the Virasoro minimal models, so that's where I'll stop for today.
Okay, so do we have any quick questions?
Okay, in the CFT, your lambda is bounded by 1. Do you have such a constraint in the bulk?
In the bulk, good question. Yeah. So the Vasiliev theories, as such, are defined for arbitrary lambda. So this HS lambda theories are defined for arbitrary lambda. The constraint on lambda from the CFT comes from unitarity, so the Vasiliev theories do not know, they are classical theories, they do not know about unitarity. So I think we believe at the moment that only the theories with lambda between 0 and 1 are dual. The Vasiliev theories with lambda between 0 and 1 are dual to unitary two-dimensional conformal field theories, while you can have classical Vasiliev theories for other values of lambda as well. They are probably not dual to unitary theories. But I think it's an interesting question whether there's some way to make sense of dual CFTs for other values of lambda in the bulk.
You mentioned in your previous talk about that you can you can violate the no-go theorem of Coleman and Mandula in AdS4.
No.
Vasiliev has shown that the Coleman-Mandula theorem can be...
No. A Coleman-Mandula theorem does not apply to conformal field theories.
No, I'm talking of the AdS4, the Vasiliev type theories.
Okay, so the Coleman-Mandula theorem does not, so the AdS, so Coleman-Mandula theorem is a statement about field theories which have higher spin.
It's explicitly in flat space, of course.
Yeah, it's a flat space description about S matrices. So I'm not sure what.
I'm just trying to understand the comment you made in the AdS4 case, that is higher spin symmetries get broken in the interacting theory, and what is the interpretation in the bulk dual of it? I mean,
the higher spin symmetries Okay, so
he's asking about
highest...
this Maldacena-Gibodaev. I think he's asking about this Maldacena-Gibodaev theorem, no-go theorem.
Yes, yeah, that's a statement about the CFT, the three-dimensional CFT.
Yeah, what is the interpretation in the bulk dual of it that in the AdS4 context that you mentioned in the slide in the AdS?
Okay.
Yeah.
So the Maldacena-Gibodaev theorem tells you that if you have strict higher spin, exact higher spin symmetry in the three-dimensional CFT, then the correlation functions of currents will be those of the free theory. Now, if you have, what I mentioned was that in these theories that were constructed recently, where you couple Chern-Simons theory, the correlation functions are not those of free theory. So the higher spin symmetry is broken. So we don't know what the bulk dual to those theories are, but whatever be the bulk dual, the higher spin symmetry would have to be broken in that theory, but by maybe in a very mild way. So in fact, from the correlation functions of the in this Chern-Simons fermion theory, you see that the violation of the higher spin currents is proportional to 1 over n. So in some ways, there's a very controlled way of expanding about the higher spin symmetric point. So my comment was that that maybe you might be able to see in the bulk what is the reflection of this controlled way of breaking the higher spin symmetry, and this would be useful for generalizing to the Yang-Mills case and higher dimensional AdS.
Okay, well, I think we should postpone any other questions for the tutorial session this afternoon. And thank Rajesh again.